Hey guys, so in this video I want to go over a little bit of the intuition as to why the complex impedance formulas for both capacitors and inductors are the way they are. And so as you can see here, I've drawn both a capacitor and an inductor, and the inductor's value is L, and I'm drawing their corresponding complex impedance formulas. So for a capacitor of some capacitance C, we have 1 over SC, and remember, the variable S is related to frequency. It's not exactly frequency, but it's related to frequency. And for an inductor with an L Henry inductor, we have SL. And so what we're going to do is we're going to actually draw the graphs 1 over SC and SL to see what they look like. So let's draw 1 over SC. So let's say we have some axes here, and I'm going to say this is S. So remember, it's related to frequency. And I'm just going to say this is value over here because we don't know what C is, so I'm just going to say for some arbitrary C we get a value out. So when S is 0, we get a 1 over 0, right? So at 0 frequency, we have basically infinite impedance. But as S increases and we get more and more frequency, we start to move out to 0 impedance. And so remembering how capacitors act physically, this graph makes sense. Because let's look at a low frequency signal, right? That's basically a DC signal. Well, in a DC signal, charge gets stored on the cap and it doesn't get removed from the cap, right? We keep moving charge and like creating unequal charge on the two plates, and as we know from our E&M class, that makes a capacitor act like a broken wire. So in that sense, having infinite impedance like a broken wire makes sense. But as we start increasing in frequency, if we had an alternating signal on a capacitor, charge is unable to build up. Yes, you might put a little bit of charge on one of the plates, but as soon as the signal reverses direction, you're going to pull that charge away. And so no voltage accumulates on this capacitor. And that means it acts just like a straight wire. And so it makes sense that as frequency gets infinite, it has 0 impedance. So now let's take a look at the inductor. So for inductor, let's draw the axes. We're going to use S again, and we're just going to use value because, just for an arbitrary L Henry inductor. So at 0 frequency, we have 0 impedance, and we go up linearly as frequency increases. And so this also makes sense because at 0 frequency, an inductor just looks like a wire. Remember, the equation for an inductor that you should remember is VL equals L di dt. So this is basically telling me if current is changing direction like a lot, you get a large voltage, which helps correspond to a large impedance. So basically, as we get more and more frequency, so as we get a more alternating frequency type signal, we get larger di dt's, which means a larger voltage generated across our inductor, and thus a larger impedance the inductor represents. And so this is a lesson that I think not a lot of people understood in my grade. They memorized these formulas, but they didn't understand why and frankly how easy it is to remember them. Because if you just remember that caps will store DC signals and act like a broken wire, thus giving them large impedances, and inductors will store energy as frequency gets higher, thus having a large impedance. You don't really have to just plain old memorize them, these formulas. You can just remember based on your intuition. So I hope this video helped, and I'll see you guys in the next one.